Tonight we drift through one of the strangest journeys the universe can offer. You are floating alone in deep space, far beyond the familiar spiral arms of the Milky Way, far beyond the glow of nearby stars, and far beyond any place a human being could realistically travel. Ahead of you hangs a black circle darker than darkness itself. Around it, distant starlight bends into glowing arcs, as though the universe has become a giant curved mirror. You are falling toward a black hole. Not a small one. Not the remnant of a dead star. This is a supermassive black hole, millions or perhaps billions of times more massive than the Sun. It sits at the center of an ancient galaxy whose stars have circled it for eons. And tonight, you are heading directly toward it. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, feel free to leave a comment sharing your location and local time. It's always fascinating to see where in the world people are listening from while we wander through the universe together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The black hole grows larger. At first, it does not seem particularly threatening. That might sound surprising. Popular movies often portray black holes as cosmic vacuum cleaners, endlessly sucking everything toward destruction. But the truth is more subtle. If our sun were magically replaced by a black hole of exactly the same mass, Earth would continue orbiting normally. The seasons would vanish because sunlight would disappear, but our orbit itself would remain nearly unchanged. Gravity depends on mass, and black holes obey gravity's rules just as planets and stars do. That is one of the first established facts you'll carry with you tonight. The universe often behaves in ways that are stranger than fiction but less dramatic than Hollywood. As you continue drifting inward, the galaxy behind you appears warped. Stars that should be hidden become visible. Constellations twist. Light curves. This effect is called gravitational lensing. The black hole's immense gravity bends spacetime itself, forcing light to travel along curved paths. Imagine placing a heavy bowling ball onto a stretched sheet. The fabric dips inward. Now imagine that sheet is not fabric at all but the geometry of reality. That image is imperfect, but it points in the right direction. The black hole is not merely sitting in space. It is reshaping space and time. The idea emerged from the work of the physicist Albert Einstein more than a century ago. His theory of general relativity described gravity not as an invisible force pulling objects together, but as the curvature of spacetime itself. At the time, even Einstein found some consequences difficult to believe. Yet the universe repeatedly proved him right. And still, black holes remain among the greatest mysteries ever discovered, because there is a boundary surrounding them. A boundary unlike anything else known. The event horizon. The point beyond which nothing can return. Not light. Not information. Not messages. Not escape plans. And certainly not that one sock that disappears in every household laundry cycle. Somewhere in the cosmos, there may be a black hole composed entirely of missing socks. Fortunately, science has not confirmed this yet. As you move closer, another strange realization settles over you. From your perspective, you are falling inward. But to a distant observer, something very different appears to happen. Suppose someone is watching from far away with an impossibly powerful telescope. They see you approaching the event horizon. Your movements slow, then slow even more. Your clock appears to tick more gradually. The color of light reflected from you shifts toward red. Eventually, you seem almost frozen. You never quite appear to cross the boundary. This is not an illusion in the ordinary sense. It emerges directly from Einstein's equations. Time itself behaves differently near extreme gravity. And already the central mystery of tonight's journey begins to reveal itself. What actually happens after you fall into a black hole? The question sounds simple, yet it sits at the intersection of nearly every great cosmic puzzle. Gravity, time, quantum mechanics, information, the origins of the universe, the fate of reality itself. For decades, scientists have tried to answer it. For decades, the answer has remained incomplete. The surprising observation is that black holes are not rare cosmic oddities. Today, astronomers believe most large galaxies contain supermassive black holes at their centers, including our own. At the heart of the Milky Way lies a black hole known as Sagittarius A star. For many years, it remained invisible. Astronomers inferred its presence by watching stars orbit something unseen. Those stars raced around an object containing millions of solar masses compressed into a tiny region. There was no other convincing explanation. In recent years, humanity even managed to capture images of black hole shadows. The pictures appeared fuzzy and glowing, not because the observations were poor, but because black holes are unimaginably difficult to photograph. You are looking at darkness surrounded by blazing matter, a silhouette against the universe. And yet even those remarkable images tell us very little about what lies beyond the horizon. The mystery remains. As your imagined journey continues, the black hole dominates the sky. The surrounding galaxy stretches into distorted ribbons. Light from distant stars loops around the darkness. Reality seems to bend around a secret. You begin to understand why black holes occupy such a unique place in science. Most objects can be observed directly. Planets reflect light. Stars emit it. Nebulae glow. Galaxies shine. But black holes reveal themselves mostly through what they hide. They are known through absence, through influence, through the strange effects they impose upon their surroundings, like footprints left by an invisible traveler. And that traveler seems to be guarding something, perhaps the most important unanswered question in modern physics. Because if information truly disappears inside a black hole, then some of our deepest theories may be incomplete. If information survives, then where does it go? If time changes near a black hole, what is time really? If spacetime can bend this dramatically, what happened during the birth of the universe itself? And if the laws of nature break down somewhere inside, what lies beyond those laws? The black hole ahead remains silent. No answers emerge from its darkness. Only questions. The oldest questions humanity has ever asked. Questions about beginnings. Questions about endings. Questions about whether reality is stranger than we currently imagine. You continue drifting closer. Slowly. Peacefully. The stars behind you shimmer across warped spacetime. The immense darkness waits ahead. And somewhere beyond that invisible boundary lies a place no human has ever seen. A place where our understanding of the cosmos becomes uncertain. A place we will approach together. For now, the event horizon remains distant. But not distant enough. And with every passing moment, the mystery grows larger. The black hole remains ahead of you. Not rushing toward you. Not lunging through space like a cosmic predator. It simply waits, enormous and silent, while you continue your gradual descent through the darkness. Behind you, the stars of the galaxy have become strangely distorted. Some appear duplicated. Others stretch into glowing arcs. The familiar geometry of space is beginning to lose its familiar shape. Yet before you venture closer to the event horizon, it helps to understand how humanity discovered that such objects could even exist. Because black holes were not found through a telescope at first. They were found through mathematics. And that is one of the most surprising things about modern astronomy. Many of the universe's strangest discoveries began as equations. Long before anyone observed a black hole, scientists were already stumbling toward the idea. The story begins in a quieter era, an era when nobody knew galaxies filled the universe, an era before spacecraft, before radio telescopes, before anyone understood that the Milky Way was only one island among trillions. Back then, gravity was described by the work of Isaac Newton. Newton's theory worked beautifully. It explained falling apples, planetary orbits, and the motions of comets. For centuries it seemed complete. Yet there was one uncomfortable question. How exactly did gravity work? Newton himself admitted he did not know. Objects appeared to influence each other across empty space. The mathematics worked perfectly, but the mechanism remained mysterious. Then, in the early 20th century, a remarkable shift occurred. Einstein introduced a radically different idea. Gravity was not a force reaching across space. Gravity was geometry. Mass and energy curved spacetime itself. Planets followed those curves. Stars followed those curves. Light followed those curves. And if enough mass became concentrated into a sufficiently small region, spacetime could become extraordinarily warped. Soon after Einstein published general relativity, a physicist named Carl Schwarzschild found an exact solution to Einstein's equations. He did so while serving during World War I. His solution described something peculiar, a region where gravity became so extreme that escape would become impossible. At first, nobody really knew what to make of it. Even Einstein suspected nature might somehow prevent such objects from existing. The equations seemed too strange, too extreme, too unreasonable. Yet nature had other plans. Decades later, astronomers began discovering stars far more massive than anyone had imagined. Some of these stars lived fast and died violently. When they exhausted their nuclear fuel, gravity could overwhelm every known force resisting collapse. The star's core would compress. Matter would squeeze inward. And under certain conditions, nothing could stop the collapse. A black hole would form. Today this idea is supported by overwhelming evidence. That is your established scientific fact for this section. Black holes are not merely mathematical curiosities. They are real astrophysical objects observed throughout the universe. Yet even now, scientists continue debating their deepest properties. As you drift closer to the giant darkness ahead, another surprising observation emerges. The universe appears far messier than expected. When astronomers began measuring galaxies, they discovered something strange. Galaxies rotated too quickly. Stars near their edges moved faster than visible matter alone could explain. According to ordinary calculations, many galaxies should have flown apart long ago. But they did not. Something unseen seemed to be holding them together. This invisible component became known as dark matter. Nobody knows exactly what dark matter is. Scientists have detected its gravitational influence repeatedly. Yet its true nature remains elusive. It neither glows nor reflects light. It does not behave like ordinary atoms. And despite decades of experiments, no one has definitively identified the particles responsible. You can think of it as one of the great hidden actors of the cosmos, a vast invisible framework upon which galaxies appear to hang. And already the mystery surrounding your black hole is beginning to connect with larger mysteries, because the universe keeps revealing that what we see is only a fraction of what exists. In fact, ordinary matter, the stars, planets, gas clouds, and everything familiar, appears to account for only a small percentage of the cosmos. The rest remains largely unknown. Imagine standing inside a vast cathedral at night with only a tiny flashlight. The illuminated area might feel significant, yet most of the structure remains hidden in darkness. That is somewhat how modern cosmology feels. Every decade reveals more knowledge. Every decade also reveals larger unknowns. As you continue your fall, the black hole's surrounding glow becomes clearer. A ring of heated matter circles the darkness. Gas spirals inward at enormous speeds. Temperatures rise to millions of degrees. The material shines brilliantly before disappearing forever. At least that is how it appears. One of the quieter jokes among astronomers is that black holes are often the brightest objects around. For something famous for being black, they certainly attract attention. The irony comes from the accretion disk, the swirling material outside the horizon. The black hole itself emits no light, but the matter falling toward it can become dazzlingly luminous. Some supermassive black holes power quasars, among the brightest objects in the observable universe. A single quasar can outshine entire galaxies. Imagine billions of stars struggling to compete with one hungry gravitational monster. Space can be unexpectedly dramatic, yet the black hole ahead remains calm, silent, patient, and as your journey continues, another layer of the cosmic stage comes into view. Time itself. In everyday life, time feels universal. A second is a second. A minute is a minute. Everyone seems to move through time together. But Einstein revealed that this intuition is incomplete. Time depends on motion and gravity. Near powerful gravitational fields, clocks run differently. This has been measured repeatedly. Even satellites orbiting Earth must account for relativistic effects to maintain accurate positioning systems. Without those corrections, modern navigation would quickly become inaccurate. Reality is already stranger than daily experience suggests, and near a supermassive black hole, those effects become profound. You are beginning to approach a region where time itself stretches, where moments no longer flow equally for every observer, where the distinction between past, present, and future becomes less obvious. Scientists can calculate many of these effects with extraordinary precision. Yet beyond a certain point, certainty begins to fade, because there is still one unresolved mystery waiting ahead: the event horizon itself. The invisible boundary separating what can communicate with the outside universe from what cannot. We know what happens outside it remarkably well. We can model the surrounding gravity. We can observe orbiting matter. We can measure light bending through spacetime. But once the horizon is crossed, confidence begins to weaken. Not because science stops working entirely, but because some of our greatest theories begin speaking different languages. General relativity describes gravity beautifully. Quantum mechanics describes the microscopic world beautifully. Yet inside black holes, those two pillars of physics refuse to cooperate completely. Somewhere ahead lies a place where they must finally meet. And nobody yet knows exactly what that meeting looks like. The darkness before you grows larger. The warped stars continue circling its edge. The horizon waits. and humanity's centuries-long attempt to understand it is only beginning. The black hole now fills a large portion of the sky. You have been falling for what feels like a long time, though already the meaning of that phrase is becoming uncertain. Around you, the distant galaxy appears twisted into luminous curves. Starlight that once traveled in straight lines now loops around the darkness ahead, tracing pathways through warped spacetime. The event horizon is no longer an abstract concept from a textbook. It is directly in front of you. And yet, strangely, nothing marks its location. There is no glowing wall, no cosmic gate, no warning sign politely informing travelers that reality is about to become extremely complicated. The universe rarely provides helpful signage. You simply approach an invisible boundary, a place where the mathematics of escape changes forever. One of the most surprising aspects of a supermassive black hole is that, at the horizon itself, you might not immediately notice anything dramatic. This sounds impossible. Popular imagination often expects instant destruction. But for a sufficiently large black hole, the event horizon can be crossed without encountering extreme local forces. That is your established scientific fact for this section. The horizon is not a physical surface. It is a geometric boundary in spacetime. If the black hole is large enough, the gravitational differences between your head and your feet at the horizon may remain relatively gentle, at least for a while. And so you continue falling. The darkness ahead grows deeper. The universe behind you appears brighter. You glance outward and see something astonishing. Time beyond the black hole seems to accelerate. The stars are still there, but their motions appear subtly altered. Imagine watching clouds move faster and faster across a sky. Imagine entire seasons unfolding in minutes. Imagine centuries passing while you observe. Near a black hole, extreme time dilation can create effects that resemble this strange vision. The deeper you move into the gravitational well, the more differently time flows compared with distant regions of the universe. This idea often feels counterintuitive because human experience evolved far from such extremes. On Earth, gravity is relatively mild. Relativistic effects exist, but they remain tiny. Near a supermassive black hole, however, spacetime itself becomes a dynamic landscape. The deeper you descend, the stranger the landscape becomes. You continue forward. No alarms sound. No sudden shock arrives. No cosmic voice announces that you have entered a restricted area. And then, without any obvious signal, you cross the event horizon. From your perspective, almost nothing special happens in that precise instant. That may be the most unsettling detail of all. The boundary that fascinates physicists around the world does not necessarily announce itself to the traveler crossing it. The realization emerges only through understanding. Not sensation. Not sight. Not touch. Understanding. Because although you can continue inward, every possible future path now leads deeper into the black hole. The horizon changes the structure of possibility itself. Outside the horizon, there are futures where you move away. Inside the horizon, every future points inward. The center is no longer merely a destination. It becomes unavoidable. An analogy sometimes used by physicists involves time itself. Here on Earth, you cannot choose to move backward into yesterday. Tomorrow lies ahead whether you wish it or not. Inside the event horizon, moving toward the center may become as inevitable as moving toward the future. The geometry of spacetime dictates the direction. And suddenly the black hole feels less like an object and more like a region where reality obeys unfamiliar rules. Looking outward, the universe becomes increasingly distorted. The light from distant galaxies appears compressed. The stars seem concentrated into smaller regions of the sky. The cosmos itself appears to gather around the shrinking window through which you can still observe it. You witness another surprising observation. In theory, enough external time could pass during your inward journey that the distant universe might age dramatically. Stars could be born. Stars could die. Galaxies could collide. Entire civilizations, if they exist elsewhere, could rise and vanish. The details depend on the specific black hole and your trajectory, but the principle remains extraordinary. Gravity influences the passage of time, and extreme gravity influences it profoundly. You drift deeper. The familiar concepts of distance begin to lose their simplicity. In ordinary life, distance feels straightforward. You measure meters, kilometers, or miles. You travel from one place to another. Near a black hole, space-time curvature complicates these intuitions. The shortest path through space-time no longer resembles the straight lines your instincts expect. The geometry itself becomes part of the story. This realization connects black holes to one of the greatest achievements in scientific history. Einstein's insight transformed space and time from passive backgrounds into active participants. The stage itself became part of the play. And nowhere is that transformation more dramatic than here. Yet even as relativity continues working beautifully, another mystery waits in the shadows. Quantum mechanics. The theory governing particles, atoms, and fundamental fields. Quantum mechanics is arguably the most successful scientific framework ever developed. Its predictions have been verified with astonishing precision. Modern electronics, lasers, and countless technologies rely on it. And yet, when quantum mechanics and black holes meet, trouble begins. Not immediately. Not here at the horizon. But deeper questions emerge. Questions that physicists still debate. For example, what happens to the quantum information carried by every particle that falls inward? According to quantum theory, information plays a fundamental role in reality. Information cannot simply vanish without consequences. Yet black holes seem remarkably good at hiding things. You can already sense the tension building. Relativity says one thing. Quantum theory says another. Both theories work. Both theories are supported by mountains of evidence. Yet somewhere ahead they appear destined to collide. And when two extraordinarily successful descriptions of reality disagree, the universe is usually trying to teach us something important. Perhaps something fundamental remains missing. Perhaps a deeper theory waits to be discovered. Perhaps black holes are pointing toward secrets hidden beneath spacetime itself. You continue descending. The outside universe now occupies a smaller portion of your view. The darkness surrounding you feels less like emptiness and more like structure. Invisible structure. Geometry beyond ordinary experience. The black hole remains silent. It offers no explanations. Only deeper questions. You think about the stars you left behind. The galaxies beyond them. The enormous web of cosmic matter stretching across billions of light years. You think about dark matter, still unidentified. Dark energy, still mysterious. The origins of the universe, still incomplete. And it becomes increasingly clear that black holes are not isolated puzzles. They sit at the crossroads of nearly every major mystery in modern cosmology. Like crossroads hidden in darkness. Like doorways whose significance is only understood after passing through them. Far behind you lies the event horizon. Far ahead lies a region no observation has ever directly explored. And somewhere between those two realms, your journey continues into one of the deepest unknown science has ever encountered. The event horizon is now behind you. Not behind you in the ordinary sense. Directions themselves have become difficult to describe here. Language evolved for forests, oceans, mountains, and skies. It did not evolve for the interior of a black hole. Still, you continue inward. The universe outside remains visible through a shrinking window of light. Distant stars flicker at the edge of perception. Entire galaxies appear compressed into strange patterns. The cosmos you have always known is still there, but it feels increasingly remote, almost like a memory. And yet, according to general relativity, you are still alive, still falling, still experiencing time. That fact alone surprises many people. Popular descriptions often imply that crossing the event horizon instantly destroys you. But for a sufficiently massive black hole, physics predicts something far stranger. You may continue your journey for quite some time. Exactly how long depends on the size of the black hole. A stellar mass black hole, formed from a collapsed star, possesses much stronger tidal forces near its horizon. A supermassive black hole spreads those forces across a larger region. That difference matters enormously. The giant black hole ahead is allowing you a longer voyage into the unknown. And so you drift deeper. The darkness does not feel empty. It feels immense. Around you, space-time itself has become the landscape. You begin noticing something difficult to explain. The center of the black hole is no longer simply a location. It behaves more like an inevitable future. Outside the horizon, you could choose different paths through space. Inside, every possible path leads inward. Imagine standing on a mountain where every road, every trail, every river, and every valley ultimately flows toward the same destination. No matter which route you take, the ending remains unchanged. That is roughly how physicists describe the geometry within a black hole. The singularity lies ahead. Or perhaps it lies in your future. The distinction becomes blurry. One lighthearted way to think about it is that you have entered the universe's least flexible travel itinerary. No alternate routes. No scenic detours. No possibility of selecting avoid toll roads. Gravity has already chosen the destination. For now, however, the singularity remains distant. And that is fortunate, because we still have much to explore. As you fall, the strange effects of spacetime become increasingly dramatic. Light behaves differently. Distances behave differently. Even causality begins to acquire unusual features. Yet Einstein's equations continue functioning with remarkable precision. This is your established scientific fact for this section. General relativity predicts the behavior of black holes extraordinarily well. From gravitational lensing to the motions of orbiting stars, observations repeatedly confirm its accuracy. The theory has passed every major test thrown at it for more than a century. And still, physicists suspect it cannot be the final story. Because hidden within its equations lies a troubling destination. The singularity. A place where density becomes effectively infinite. A place where curvature becomes infinite. A place where the mathematics itself appears to break down. Most scientists do not believe nature literally contains infinities in the simple way the equations suggest. Instead, infinities often signal that a theory has reached its limits. The map no longer describes the territory. The equations no longer tell the complete story. And so the singularity becomes less of an answer and more of a warning sign. It tells us that something remains undiscovered. As you continue falling, Another surprising observation emerges. Black holes may be among the simplest objects in the universe, at least from the outside. This idea sounds absurd. After all, you are currently inside one of the most mysterious structures known to science. Yet physicists discovered that black holes can often be described using only a few basic properties: mass, charge, angular momentum. That is essentially it. Everything else seems hidden. The countless details of the stars, gas clouds, planets, atoms, and particles that form the black hole appear to vanish behind the horizon. Imagine shredding every book ever written, every photograph ever taken, every piece of music ever composed, and somehow ending up with a single identical black sphere regardless of what went in. That would seem impossible. Yet black holes appear to behave in a surprisingly similar way. This simplicity eventually led to one of the greatest mysteries in theoretical physics, a mystery we will soon encounter directly. But first, your journey continues inward. The shrinking view of the universe outside grows stranger. Time beyond the black hole seems increasingly accelerated. The stars you once recognized no longer occupy familiar positions. Galactic structures evolve. Ancient light shifts. The cosmos appears to age before your eyes. Exactly how much of this effect would occur in practice remains complicated, but the principle is real. Strong gravity alters the relationship between observers and time, and black holes represent the most extreme laboratories for studying that relationship. You find yourself wondering about the distant future. Will the stars still shine? Will galaxies remain separate? Will dark energy continue stretching space apart? Will intelligent civilizations survive long enough to understand these mysteries? No one knows. The black hole provides no answers, only perspective. From here, the entire history of humanity seems astonishingly small. Civilizations rise and fall in mere moments compared with cosmic timescales. Empires vanish. Languages disappear. Continents reshape themselves. Stars endure. Galaxies endure longer. The universe measures time using scales that dwarf human imagination. And yet, despite those vast spans, even the cosmos appears temporary. Stars burn fuel. Galaxies evolve. Black holes themselves may eventually evaporate. Nothing appears permanent. That realization carries a peculiar calmness. Everything changes. Everything transforms. Even the largest structures known. As your descent continues, another unresolved mystery begins to emerge from the darkness. What if the singularity is not the end? What if Einstein's equations fail before reaching it? What if quantum effects become dominant? Some researchers have proposed quantum cores, quantum bounces, or entirely new states of matter. Others suggest spacetime itself may possess a microscopic structure invisible at ordinary scales. At present, these ideas remain speculative. No observation has confirmed them. But neither can current physics fully describe what happens at the center. The mystery remains open. And perhaps that openness is the most important clue of all. Whenever science encounters a boundary of understanding, new discoveries often follow. The atom once seemed indivisible. Then it wasn't. The Milky Way once seemed to contain the entire universe. Then it didn't. Space and time once appeared absolute. Then Einstein showed otherwise. Perhaps black holes represent another such turning point, a place where a deeper layer of reality waits to be uncovered. You continue falling. The singularity remains ahead. The universe remains behind. And somewhere between them lies one of the most profound unanswered questions in all of science. Not what happens outside a black hole, not what happens at the horizon, but what happens after. The singularity remains ahead, not visible, not glowing, not announcing its presence. It exists more as a prediction than a destination you can actually see. The deeper you travel into the black hole, the more apparent it becomes that your journey is no longer merely about falling through space. You are approaching the edge of what human knowledge can confidently describe. Up to this point, general relativity has guided you remarkably well. It explained the bending of light. It explained time dilation. It explained the event horizon. It explained why your path inward became unavoidable. Yet now the theory begins leading you toward something uncomfortable, an infinity. And physicists tend to become suspicious whenever infinities appear. Not because infinities are impossible, but because they often signal that a theory has reached territory it was never designed to explain. Imagine using a map of a city to navigate the entire planet. The map might work beautifully for a while. Then eventually it would fail. Not because the map is wrong, because its domain is limited. Many scientists suspect something similar is happening inside black holes. General relativity may be an extraordinarily accurate map, but perhaps not the final one. You continue inward. The outside universe now occupies only a tiny region of your view. The stars appear compressed into an increasingly concentrated patch of light. The vast cosmos that once surrounded you has become a distant window. And that shrinking window inspires a surprising observation. From everything astronomers currently understand, the observable universe itself possesses horizons. Not black hole horizons, but cosmic horizons. There are regions so distant that their light has not yet reached us. There are places forever hidden by the expansion of space. In a strange way, every observer inhabits a limited bubble of reality. No matter how powerful our telescopes become, some parts of the universe may remain permanently beyond observation. That realization connects your journey inside a black hole to a much larger cosmic truth. Knowledge itself has horizons, not just in space, not just in time, but in understanding. Still, scientists continue pushing those boundaries. And nowhere are those efforts more intense than in the search for a theory of quantum gravity. This is your established scientific fact for this section. Modern physics rests on two enormously successful foundations. General relativity describes gravity and large-scale structure. Quantum mechanics describes microscopic reality. Each theory works spectacularly within its own domain. Yet combining them completely remains one of science's greatest unsolved challenges. Black holes sit directly at the intersection of both. And because of that, they may hold clues to a deeper theory. You drift onward. Imagine shrinking yourself smaller and smaller. Past planets, past mountains, past grains of sand, past molecules, past atoms, past atomic nuclei. Eventually, you enter a realm governed almost entirely by quantum rules. Particles behave like waves. Probabilities replace certainties. Empty space turns out not to be truly empty. Instead, quantum fields ripple throughout the vacuum. Tiny fluctuations emerge and disappear continuously. Reality becomes less solid than everyday intuition suggests. This microscopic world seems enormously distant from black holes. Yet surprisingly, the two may be intimately connected. Some physicists suspect spacetime itself could possess a quantum structure. Perhaps space is not infinitely smooth. Perhaps time is not infinitely continuous. Perhaps both are woven from something deeper, something more fundamental, something we have not yet discovered. One of the gentler jokes in theoretical physics is that every time researchers think reality cannot become any stranger, reality accepts that as a personal challenge. The universe has consistently won this competition. You continue falling. The singularity still lies ahead, at least according to classical theory. Yet quantum ideas offer alternative possibilities. Some researchers propose that collapse never reaches an actual infinity. Instead, quantum effects may halt the process before that point. Others imagine incredibly dense quantum states unlike anything observed elsewhere. Some speculate about Planck-scale structures where spacetime itself becomes grainy. These ideas remain hypothetical. No observation has yet confirmed them. But they illustrate something important. Scientists are not merely trying to solve a black hole problem. They are trying to understand the fundamental architecture of reality. And that architecture may be stranger than anything currently imagined. As you descend deeper, another mystery emerges. Where did black holes first come from? The obvious answer is dying stars. Many black holes certainly formed that way. Yet astronomers have discovered supermassive black holes in the early universe. Some appeared astonishingly soon after cosmic history began. So soon, in fact, that researchers still debate how they grew so quickly. This remains an unresolved mystery. How did some black holes become gigantic in such a short time? Did they begin from unusually massive seeds? Did exotic processes operate during the universe's infancy? Or are we missing part of the story entirely? The question matters because black holes seem deeply connected to galaxy formation itself. Nearly every large galaxy we examine appears to host a supermassive black hole. The relationship may not be coincidental. Galaxies influence black holes. Black holes influence galaxies. A complex cosmic partnership stretches across billions of years. You begin thinking about origins. The origin of black holes. The origin of stars. The origin of matter. The origin of space and time. And inevitably, your thoughts drift toward the greatest beginning of all. The Big Bang. The early universe was unimaginably dense, unimaginably hot. In some respects, physicists studying the Big Bang confront challenges similar to those encountered inside black holes. The known laws of physics approach extreme conditions. Certainty becomes harder to maintain. Theories become incomplete. Mysteries multiply. It is almost as though the beginning of the universe and the interior of black holes occupy neighboring chapters of the same unfinished book. Both point toward physics beyond current understanding. Both suggest hidden layers beneath familiar reality. Both challenge humanity's deepest assumptions. As the darkness around you grows more profound, another possibility appears. What if black holes are not merely endpoints? What if they participate in larger cosmic processes? Over the decades, some speculative theories have imagined black holes spawning new universes. Others suggest connections between black holes and wormholes. Some propose that our own universe might somehow be linked to structures resembling black holes. At present, there is no evidence confirming such ideas. They remain fascinating possibilities rather than established science. Yet their existence reveals how powerful the mystery has become. Black holes force us to ask questions extending far beyond astronomy. Questions about creation. Questions about reality. Questions about existence itself. And still, the deepest puzzle has not yet arrived. Because even if the singularity can be replaced by new physics, even if quantum gravity eventually resolves the infinities, one stubborn problem remains. A problem that has occupied some of the greatest minds in modern science. A problem concerning information, the most ordinary thing imaginable, and perhaps the most important thing in the universe. The question is deceptively simple. If you fall into a black hole, what happens to the information that makes you you? The answer, surprisingly, may determine how reality itself works. The deeper you travel into the black hole, the more one question begins to overshadow all the others. Not what happens to your body, not what happens to matter, not even what happens to spacetime. What happens to information? At first, the question sounds oddly technical, perhaps even a little disappointing. After all, you are falling through one of the most mysterious environments in existence, and physicists want to talk about information. But in modern science, information is not merely data stored on a computer. It is something far more fundamental. Every particle carries information. Every atom carries information. Every arrangement of matter contains information about its state. The positions of particles, their energies, their quantum properties, their relationships to one another. Reality itself can be viewed, in part, as an intricate tapestry of information. And according to quantum mechanics, that tapestry follows very strict rules. One of the most important is that information should not simply vanish. It can change form. It can become difficult to recover. It can spread throughout a system. But fundamentally, quantum theory suggests that information is preserved. This is your established scientific fact for this section. Quantum mechanics describes physical processes using equations that conserve information. And therein lies the problem. Because black holes appear to do the opposite. Imagine tossing a library into a black hole. Every book, every page, every word, every idea. From the outside, the black hole grows slightly more massive. Yet all the details seem lost. Now imagine throwing in an entire civilization. Its art, its music, its languages, its history, its dreams. Again, the black hole merely gains a bit more mass. The details disappear from view. Eventually, it seems as though the black hole has erased them. And physicists dislike erasure. Not because they are sentimental about libraries, though many probably are, but because erasing information appears to violate the fundamental rules of quantum theory. For decades, this conflict has become one of the most famous puzzles in modern physics. The black hole information paradox. You continue drifting through the darkness while the paradox unfolds around you like a cosmic detective story. The trouble became especially intriguing during the 1970s. Before then, black holes were often imagined as perfect traps. Anything entering would remain forever hidden. Simple, mysterious, final. Then, a remarkable development changed everything. The physicist Stephen Hawking combined ideas from quantum mechanics and general relativity. The result shocked the scientific community. Black holes, he discovered, are not entirely black. They emit radiation. Today, this phenomenon is known as Hawking radiation. The basic idea is subtle. Quantum fluctuations constantly occur throughout space. Even empty vacuum contains activity at microscopic scales. Near an event horizon, these quantum effects can lead to the gradual emission of energy. Over immense periods of time, the black hole slowly loses mass. Eventually, it may evaporate completely. This surprising observation transformed black holes forever. They were no longer eternal prisons. They became temporary objects, long-lived beyond imagination certainly, but not permanent. And suddenly a much bigger mystery appeared. If the black hole eventually evaporates away, what happens to everything that fell inside? Where does the information go? You can almost feel the universe smiling quietly at this point. Just when scientists thought they understood the problem became larger. Theoretical physics occasionally resembles a hallway where every open door reveals 3 additional locked doors. The black hole information paradox became one of those doors. If information truly disappears, quantum mechanics faces a serious challenge. If information survives, then somehow it must escape the black hole's apparent secrecy. Both possibilities create difficulties. For decades, researchers debated fiercely. Entire careers became devoted to the question. Countless papers appeared. New hypotheses emerged. Old assumptions were challenged. Yet no universal consensus fully settled the matter. Several fascinating ideas arose. One proposal suggests that information somehow becomes encoded within Hawking radiation itself. Not destroyed, not lost, merely scrambled beyond easy recognition. Imagine taking an enormous encyclopedia and feeding it into a blender. The information technically still exists, but reconstructing it becomes unimaginably difficult. Perhaps black holes operate similarly. Another possibility involves subtle quantum correlations spread throughout the radiation. Others invoke holographic principles, suggesting that information may be stored on surfaces rather than volumes. These ideas remain areas of active research. Some enjoy substantial theoretical support. None have yet provided a final universally accepted answer. And that unresolved mystery accompanies you deeper into the darkness. The question becomes surprisingly personal. After all, you are not merely an observer. In this thought experiment, you are the one falling inward. Every memory, every experience, every thought, every childhood moment, every conversation, every dream, all encoded within physical systems, all represented by information. Could that information truly disappear? Or does reality preserve it somehow? The universe refuses to answer directly. Instead, it offers clues. And some of those clues lead to even stranger territory. In recent years, physicists have begun uncovering unexpected connections between black holes, quantum information, and spacetime itself. Some researchers now suspect that spacetime may emerge from deeper informational relationships. In other words, information might not merely describe reality. It might help create it. This idea remains speculative, yet it has become increasingly influential. The possibility is astonishing. Perhaps black holes are not simply objects hidden within spacetime. Perhaps they reveal how spacetime is constructed in the first place. As you continue inward, the darkness around you feels different. Less like emptiness, more like concealment, as though the universe has folded a corner of its blueprint out of sight. Another surprising observation appears. The equations describing black holes often connect seemingly unrelated branches of physics. Gravity, thermodynamics, quantum theory, information science, geometry. They all converge here. It is as though black holes occupy a crossroads where multiple roads through reality intersect. And whenever different fields suddenly begin pointing toward the same destination, scientists pay close attention, because such convergences often signal deeper truths. You drift onward. The singularity remains uncertain. The information paradox remains unresolved. The quantum nature of spacetime remains unknown. And yet the mystery continues expanding, because black holes are no longer the only strange structures demanding explanation. Beyond them lie other possibilities. White holes, wormholes, dark matter halos, invisible cosmic architectures, perhaps even phenomena not yet imagined. The universe is not content with one mystery. It appears determined to collect them. And somewhere among those mysteries may lie the answer to what truly happens after you fall into a black hole. Or perhaps the answer leads somewhere even stranger. Somewhere beyond black holes entirely. The black hole has already transformed from an object into a question about gravity, a question about information, a question about the architecture of reality itself. But now, as you continue your impossible journey inward, something unexpected happens. The mystery expands beyond black holes. Far beyond. The deeper physicists investigate these strange cosmic objects, the more they discover connections reaching into other unsolved puzzles scattered throughout the universe. It is as though black holes sit at the center of an enormous web. Pull one thread, and distant mysteries begin to move. You drift through darkness while that web gradually reveals itself. The first thread leads toward dark matter. For decades, astronomers have known something invisible surrounds galaxies. Stars orbit too quickly. Galaxy clusters hold together too strongly. Gravitational lensing appears more intense than visible matter can explain. Again and again, observations point toward unseen mass. This is your established scientific fact for this section. Dark matter has never been directly identified, yet its gravitational effects are observed throughout the cosmos. Scientists estimate that ordinary matter, the stars, planets, gas clouds, and people, makes up only a small fraction of the universe's total mass-energy content. The rest remains largely hidden. That realization remains one of the most humbling discoveries in science. Everything humanity has ever touched belongs to the minority component of reality. We appear to live inside a universe mostly composed of things we do not yet understand. Naturally, black holes became suspects. Could dark matter somehow consist of black holes? The idea has been explored repeatedly, particularly in the case of hypothetical primordial black holes. These would not form from dying stars. Instead, they might have emerged during the extraordinarily dense conditions of the early universe. Tiny fluctuations shortly after the Big Bang could, in principle, have created black holes of various sizes. If enough survived until today, perhaps they contribute to dark matter. It is an intriguing possibility. Yet observations have placed significant limits on many versions of the idea. Some ranges remain open for investigation. Others appear increasingly unlikely. The mystery remains unresolved. And that uncertainty keeps researchers searching. You continue inward. The darkness around you seems almost symbolic now. Every answer reveals another hidden layer. Every discovery uncovers another unseen structure. The next thread leads toward wormholes. Of all the concepts associated with black holes, few capture public imagination more effectively. A wormhole is often described as a shortcut through spacetime. Instead of traveling across vast cosmic distances, one might theoretically pass through a tunnel connecting distant regions. General relativity allows mathematical solutions resembling such structures. That much is true. Whether traversable wormholes actually exist is another matter entirely. At present, no evidence confirms their existence. That distinction is important. Science has not discovered a functioning cosmic tunnel network quietly waiting beyond Jupiter. As entertaining as that would make space travel, still wormholes occupy an intriguing place in theoretical physics. Some solutions connect black holes to white holes. Others suggest bridges between distant regions of spacetime. Most encounter significant stability problems. Many appear unlikely to survive in realistic conditions. Yet the possibility continues inspiring investigation. And black holes remain deeply connected to those discussions. You imagine for a moment that your journey inward does not end at a singularity. Instead, spacetime folds. The darkness opens. A distant region of the cosmos appears. Perhaps another galaxy. Perhaps another universe. Perhaps somewhere entirely beyond current understanding. This remains speculation. But it illustrates how black holes encourage physicists to explore possibilities extending beyond conventional assumptions. The universe becomes larger every time we question it carefully. You continue drifting. The shrinking window of stars behind you has become extraordinarily distant. Yet another mystery waits beyond it. White holes. If a black hole allows matter to enter but not escape, a white hole would represent the opposite. Matter could emerge. Nothing could enter. Mathematically, such solutions can arise within relativity. Observationally, however, no confirmed white hole has ever been discovered. Their existence remains hypothetical. Still, they occupy a fascinating role in discussions about cosmic symmetry. Nature often displays balance. Positive and negative charges. Matter and antimatter. Action and reaction. Could black holes possess counterparts? No one knows. The possibility remains one of many open questions lingering at the frontier. Then the mystery expands further. Beyond black holes. Beyond wormholes. Beyond white holes. Toward the universe itself. Because even if every black hole mystery were solved tomorrow, another enormous puzzle would remain waiting. Dark energy. The name sounds almost poetic. Yet it emerged from one of the most surprising discoveries in modern astronomy. Scientists expected cosmic expansion to slow over time due to gravity. Instead, observations revealed something astonishing. Expansion is accelerating. Galaxies are moving apart faster and faster. Something appears to be pushing the universe outward. Nobody knows exactly what that something is. Dark energy became the label for this unknown phenomenon. And remarkably, it may represent the majority of the universe's total energy content. Think about that for a moment. Most matter is mysterious. Most energy is mysterious. And we are trying to understand black holes within this already mysterious universe. The cosmic puzzle keeps getting bigger. A light-hearted joke seems appropriate. Astronomy occasionally resembles opening a refrigerator to investigate a missing sandwich and discovering that most of the house is missing as well. The original mystery never disappears. It simply becomes part of a larger one. You continue inward. And now the conversation turns toward something even stranger. Cosmic anomalies. Observations that refuse to fit comfortably within expectations. Throughout the history of astronomy, unexpected measurements have repeatedly driven scientific progress. Sometimes anomalies disappear with better data. Sometimes they reveal revolutionary discoveries. The orbit of Mercury helped inspire relativity. Unusual galaxy motions helped reveal dark matter. Unexpected cosmic acceleration led to dark energy. Today, researchers continue studying puzzling observations. Strange alignments. Unusual gravitational behavior. Rare energetic events. Fast radio bursts appearing from distant galaxies. Structures so large they challenge assumptions about cosmic uniformity. Most eventually find explanations. Some remain unresolved. And every unresolved mystery invites another question. Could black holes connect to phenomena we have not yet recognized? Could they influence the large-scale evolution of the cosmos? Could they provide clues to the earliest moments after the Big Bang? The answers remain uncertain. But increasingly, black holes appear less like isolated objects and more like gateways into deeper scientific questions. Not gateways in the science fiction sense. Gateways of understanding. Places where familiar theories become insufficient. Places where hidden connections emerge. Places where the universe quietly hints that there is more to learn. You drift deeper into the darkness. The black hole still surrounds you. The information paradox remains unresolved. Dark matter remains unidentified. Dark energy remains mysterious. Wormholes remain hypothetical. White holes remain unseen. And somehow, instead of shrinking, the mystery continues growing. The farther you travel, the larger reality appears. And soon, even the black hole itself will become only one piece of a much grander puzzle. The black hole is no longer the center of the story. Or perhaps it is. That is becoming increasingly difficult to determine. Because every road you follow from the black hole seems to lead outward into larger and larger mysteries. You began this journey by asking what happens after you fall through an event horizon. Now you find yourself confronting questions about the entire universe. Questions about its birth, its growth, its hidden ingredients, its eventual fate. The deeper you descend into one mystery, the more all mysteries seem connected. The darkness around you feels almost symbolic now. A reminder that knowledge is illuminated only in patches. Beyond every circle of understanding lies a larger ocean of unknowns. And nowhere is that more apparent than when we look at the earliest moments of cosmic history. Long before stars existed. Long before galaxies formed. Long before black holes appeared. The universe itself emerged from conditions unlike anything we experience today. This is your established scientific fact for this section. Observations strongly support that the universe was once much hotter, denser, and more uniform than it is now. Evidence comes from cosmic expansion, the abundance of light elements, and the cosmic microwave background radiation. That faint glow still fills space today. It is ancient light, a relic from a time when the universe was only a few 100,000 years old. In a sense, astronomers possess a baby picture of the cosmos, and that picture contains mysteries of its own. As you drift through the darkness, imagine the young universe. No planets, no stars, no galaxies. Only a vast sea of hot particles and radiation. Tiny fluctuations ripple through the primordial plasma. At first glance they seem insignificant. Yet over billions of years, gravity amplifies those tiny differences. The denser regions attract more matter. Structures begin forming. Eventually, galaxies emerge. Clusters emerge. The cosmic web takes shape. Everything familiar traces its origins back to those nearly invisible fluctuations. And yet one crucial question remains unresolved. Why did those fluctuations exist at all? Scientists have developed powerful ideas to explain the early universe. One of the most influential is cosmic inflation. According to this hypothesis, the universe underwent an extraordinarily rapid expansion during its earliest moments. A tiny region became vastly larger in an unimaginably short period. Inflation successfully explains many observed features of the cosmos. Yet the deeper cause of inflation remains uncertain. What triggered it? What ended it? What came before it? Nobody knows. The mystery remains open, and it stretches far beyond black holes. You continue inward, or perhaps outward. The distinction has become increasingly philosophical. The singularity you once imagined ahead now feels connected to the beginning of everything. Both involve extreme conditions. Both involve incomplete theories. Both seem to point toward physics beyond current understanding. Some researchers have even remarked that studying black holes and studying the early universe often feels like examining opposite sides of the same coin. One concerns collapse. The other concerns expansion. Yet both reveal the limits of existing knowledge. The universe appears determined to hide its deepest secrets behind extremes. Another surprising observation emerges. The largest structures in existence are astonishingly vast. Galaxies gather into clusters. Clusters gather into superclusters. Immense filaments of matter stretch across hundreds of millions of light years. Between them lie enormous cosmic voids, regions where relatively little matter exists. If you could zoom outward far enough, the universe would resemble an intricate web, a network spanning unimaginable distances. And despite decades of observation, astronomers continue finding structures so large they challenge expectations. Not necessarily because theories are wrong, but because reality often turns out more complicated than anticipated. One gentle truth about science is that certainty rarely arrives all at once. Progress usually comes through gradual refinement, question after question, discovery after discovery, mystery after mystery. You think about the civilizations that may exist elsewhere. The possibility feels natural here. After all, the Milky Way alone contains hundreds of billions of stars. The observable universe contains trillions of galaxies. The numbers become almost impossible to visualize. Many stars possess planets. Many planets occupy potentially habitable regions. The ingredients for life appear widespread. Yet despite decades of searching, no confirmed extraterrestrial civilization has been detected. This unresolved mystery is often called the Fermi paradox. Where is everybody? The question remains surprisingly difficult. Perhaps intelligent life is rare. Perhaps civilizations are short-lived. Perhaps communication across cosmic distances proves extraordinarily difficult. Perhaps we have simply not looked long enough. No one knows. And once again, the universe offers possibilities rather than conclusions. As you continue drifting through darkness, another possibility emerges. What if our universe itself is only part of something larger? The idea appears in various theoretical frameworks. Certain models of inflation suggest multiple universes could exist. Some interpretations of quantum mechanics invite related discussions. Others explore entirely different possibilities. At present, these concepts remain speculative. There is no direct evidence proving a multiverse. Yet the fact that respected theories sometimes point in that direction illustrates how expansive modern cosmology has become. Questions once considered philosophical now intersect with mathematical physics. And black holes often appear somewhere in those conversations, not because they provide answers, but because they expose limitations. They force us to confront gaps in understanding. They remind us that reality may possess layers we have not yet uncovered. The darkness surrounding you feels calmer now, less threatening, more contemplative. The black hole that began this journey has become a lens through which the entire cosmos can be viewed. Its mysteries connect to inflation, to dark matter, to dark energy, to quantum theory, to the origins of galaxies, to the possibility of other universes, and perhaps most importantly to the limits of human knowledge itself. A second light joke drifts quietly through your thoughts. The universe seems remarkably committed to avoiding straightforward explanations. If cosmic mysteries were employees, they would all be winning awards for workplace persistence. Still, scientists continue searching, observing, calculating, questioning, because every mystery solved reveals something profound, and every mystery unsolved points toward future discoveries. You continue drifting through the darkness. The stars remain far behind. The singularity remains uncertain. The universe remains unfinished. And ahead lies perhaps the deepest question of all. Not how the cosmos works, but what it means that a cosmos exists in the first place. The darkness feels different now, not because it has changed, but because you have. When this journey began, the black hole seemed like a destination, a fascinating object hidden somewhere in deep space, a cosmic mystery waiting to be explored. Now it feels more like a mirror. The deeper you have traveled into its questions, the more those questions have turned back toward you. What happens after you fall into a black hole? Somewhere along the way that became another question entirely. What is time? What is reality? What does it mean to exist inside a universe capable of wondering about itself? You continue drifting. The distant stars remain visible only as faint traces now. The familiar cosmos appears unimaginably far away. And yet, in another sense, it has never been closer, because nearly every mystery you have encountered seems connected. Black holes, dark matter, dark energy, quantum mechanics, the beginning of the universe, the fate of the cosmos. Each appears to be a separate puzzle. Yet sometimes science advances by discovering that several puzzles are actually pieces of one larger picture. Perhaps that is true here as well. Perhaps not. For now, nobody knows. And that uncertainty leads naturally into one of the oldest questions humanity has ever asked. What is time? This is your established scientific fact for this section. Modern physics treats time very differently than everyday intuition does. According to relativity, time is not universal. It does not flow identically for all observers. Its passage depends on motion and gravity. This has been experimentally confirmed countless times. Clocks at different speeds tick differently. Clocks in different gravitational environments tick differently. Time is real, yet it is not as absolute as it appears. That realization alone would have astonished most people throughout human history. For thousands of years, time seemed obvious. A river flowing steadily forward. A cosmic clock shared by everyone. Einstein revealed something stranger. Time behaves more like a dimension woven together with space. Flexible, dynamic, responsive, and near black holes, that flexibility becomes impossible to ignore. You imagine all the moments of your life spread across spacetime. Childhood afternoons, quiet conversations, moments of joy, moments of uncertainty, countless ordinary experiences. Physics describes them not merely as memories but as events occupying locations within spacetime. The thought feels oddly comforting. The past is gone from your perspective. Yet in another sense, it remains part of the universe's structure, embedded within the history of reality. And then another question emerges. Why does time seem to move in one direction? Physics often works equally well forward and backward. Yet everyday experience possesses a clear arrow. You remember yesterday. You do not remember tomorrow. A dropped glass shatters. The shards do not spontaneously reassemble themselves. Scientists generally connect this arrow of time to entropy, the tendency for disorder to increase. Yet even this explanation ultimately traces back to the remarkable conditions of the early universe. Why did the universe begin in such a low entropy state? Why was cosmic history arranged in a way that allowed complexity to emerge? That remains an unresolved mystery, one of the deepest in all of science. You drift onward. The darkness surrounding you feels almost peaceful, no longer merely a place of ignorance, a place of possibility, a place where questions can exist without immediate answers. Perhaps that is one reason black holes fascinate us so deeply. They remind us that mystery is not failure. Mystery is often where discovery begins. You think about consciousness, not as a mystical force, not as a supernatural phenomenon, simply as the experience of being aware, the experience you are having right now, the experience of observing, wondering, reflecting. Science has made enormous progress in understanding the brain, yet consciousness itself remains difficult to fully explain. How does subjective experience arise from physical processes? How do particles and fields give rise to awareness? Researchers continue investigating these questions. No consensus exists. And once again, the universe presents another frontier, another horizon, another place where knowledge remains incomplete. A surprising observation comes to mind. The atoms in your body were forged inside ancient stars. The carbon, the oxygen, the calcium, the iron, all created through cosmic processes unfolding long before Earth existed. In a literal sense, you are made from stellar history. You are a temporary arrangement of matter that has learned to contemplate the universe that produced it. When viewed this way, consciousness becomes one of the strangest phenomena in existence. The cosmos has somehow generated beings capable of asking why the cosmos exists. No wonder philosophers have spent centuries pondering the implications. One gentle joke seems appropriate. The universe spent nearly 14 billion years creating stars, galaxies, black holes, and quantum fields, only to end up with a species that occasionally forgets why it walked into a room. Reality clearly appreciates irony. You continue drifting. The black hole remains mysterious. Yet perhaps the greatest mystery is not hidden inside it. Perhaps the greatest mystery is that anything exists at all. Why is there something rather than nothing? The question sounds simple, almost childlike, yet it reaches astonishing depth. Every scientific explanation typically relies upon deeper laws, deeper structures, deeper assumptions. Eventually, we arrive at a boundary. Why do those laws exist? Why does reality possess the properties it does? Could things have been different? Are there countless possible universes? Or only one? At present, Science does not possess definitive answers. And perhaps that is perfectly acceptable. The goal of inquiry is not always immediate resolution. Sometimes the goal is understanding the shape of the mystery itself. Black holes have helped reveal that shape. They have shown us where theories meet, where assumptions break down, where hidden connections emerge. They have reminded us that reality remains larger than our current explanations. And yet that realization does not diminish human achievement. Quite the opposite. Think about what humanity has already accomplished. A species living on a small rocky planet has measured the age of stars, mapped distant galaxies, detected gravitational waves, photographed black hole shadows, decoded ancient cosmic light, all while orbiting an ordinary star in a modest corner of the Milky Way. That is extraordinary. We understand vastly more than our ancestors did. And still the deepest questions remain open. Perhaps they always will. Perhaps every answer generates new mysteries. Perhaps knowledge is not a destination but an endless horizon. Like the event horizon that began this journey. Always inviting us forward. Always revealing something beyond. You continue drifting through the darkness. Calmly. Quietly. Toward one final reflection. Toward the original question. Toward the horizon that still refuses to surrender all its secrets. The black hole is still with you. After everything you have seen, everything you have considered, everything you have imagined, the great darkness remains. Silent, patient, unanswered. You began this journey with a simple question. What happens after you fall into a black hole? It sounded like a question about an object, a destination, a cosmic curiosity hidden somewhere among the stars. But along the way, the question unfolded into something far larger. You discovered that black holes are not merely regions of extreme gravity. They are crossroads. Places where our best descriptions of reality intersect. Places where certainty begins to thin. Places where the known universe gradually gives way to deeper mystery. You remember the event horizon. That invisible boundary where escape becomes impossible. You remember the warped starlight bending around the darkness. The strange behavior of time. The shrinking view of the outside universe. The possibility that information may never truly disappear. The unresolved questions surrounding quantum gravity. The mysteries of dark matter. The puzzle of dark energy. The echoes of the Big Bang. The possibility that spacetime itself may be more complex than anyone currently understands. All of those threads remain unfinished. And perhaps that is the most honest conclusion available. Science has not solved the mystery of what happens after you fall into a black hole. Not completely. Some parts are understood remarkably well. General relativity provides extraordinarily accurate predictions. Observations continue confirming its success. Black holes exist. Event horizons exist. Gravitational lensing exists. Time dilation exists. These are not guesses. They are among the most well-supported ideas in modern science. This is your established scientific fact for this section. Yet beyond those achievements, questions remain. Important questions. Profound questions. Questions that may ultimately reshape our understanding of reality. Perhaps information escapes through subtle quantum processes. Perhaps spacetime possesses a hidden microscopic structure. Perhaps singularities never truly form. Perhaps entirely new physics waits beyond the limits of current theories. Nobody knows for certain. The universe has not yet revealed the answer. And so, in a sense, you remain suspended between knowledge and mystery, just as humanity does. That image feels appropriate, because the history of science has always unfolded this way. Every generation pushes a little farther into the darkness. Every generation discovers something remarkable. Every generation also discovers that the unknown extends beyond the newly illuminated horizon. The mystery never disappears. It simply changes shape. You think again about the earliest humans who looked upward into the night sky. They saw stars, patterns, legends, questions. They could not have imagined galaxies, black holes, quantum fields, expanding spacetime. Yet the curiosity itself was already present, the same curiosity that carried humanity through centuries of observation and discovery, the same curiosity that continues today, the same curiosity that brought you here, to the edge of a black hole, to the edge of understanding, to the edge of a question that remains beautifully incomplete. And perhaps that incompleteness is not disappointing. Perhaps it is inspiring, because every unanswered question represents an invitation to keep exploring, to keep observing, to keep wondering. The black hole ahead offers no final revelation, no hidden message, no ultimate explanation, only silence. But sometimes silence has its own meaning. Sometimes it reminds us how vast reality truly is. The darkness feels peaceful now, not empty, not threatening, simply vast, a place where knowledge ends and possibility begins. You drift there for a while, watching, waiting, listening, and gradually the journey begins to soften. The questions remain. The universe remains. The mystery remains. But there is no urgency, no rush toward conclusions. Only the quiet awareness that some answers take time, perhaps cosmic time, perhaps longer. And now, as the journey draws to a close, the universe itself seems to slow. The stars return. The galaxies return. The great black hole remains at the center of the darkness. And the final wind down begins. The stars shine across distances so vast that human history becomes almost invisible beside them. Ancient starlight continues traveling through space, crossing millions and billions of years before reaching distant observers. Some of those stars are young. Some are old. Some have already vanished, leaving only their light to continue the journey. Around them, galaxies drift through the cosmic web. Spiral galaxies, elliptical galaxies, dwarf galaxies, countless islands of light suspended within an ocean of darkness. At the hearts of many of them sit black holes. Quiet, massive, patient. Some feed on surrounding matter. Others rest almost unnoticed. All remain among the strangest objects ever discovered. And beneath the scale of stars and galaxies, another universe unfolds. A universe of quantum particles, tiny fluctuations, invisible fields, microscopic events that shape the structure of everything larger. The smallest scales and the largest scales remain connected in ways we do not yet fully understand. Black holes seem to stand between those realms. 1 foot in gravity, 1 foot in quantum reality. A bridge between mysteries. Above them all stretches cosmic time. Billions of years behind. Billions of years ahead. Stars are born. Stars fade. Galaxies collide. Black holes grow. Black holes may eventually evaporate. Even the universe itself will continue changing long after every familiar landmark has transformed. And yet, despite all that change, the questions endure. What happened at the beginning? What happens inside a black hole? What is dark matter? What is dark energy? Why does reality exist? The answers remain hidden. For now. But humanity has already come remarkably far. We understand far more than our ancestors ever did. Yet the deepest secrets remain hidden, perhaps somewhere beyond an event horizon, perhaps within quantum spacetime, perhaps in regions of the cosmos we have not yet explored, or perhaps in ideas not yet imagined. For tonight, it is enough simply to appreciate the mystery. The stars continue shining. The galaxies continue drifting. The black holes continue waiting. The quantum particles continue dancing through the fabric of reality. And cosmic time continues flowing onward into the unknown. You drift quietly among them, peaceful, small, curious, part of the story. And the story continues.